Hey everyone, my name is Mitchell. I'm a machine learning engineer at Comma, and I'm going to talk a bit today about all the work we've done to ship Navigator on OpenPilot. So this is a project we've been working on for a while. I think I started on this late last year, and then we showed off an initial version of Navigate in our Driving to Taco Bell video at the end of last year. The idea is, well, the driving model already takes the videos from the two cameras on the Comma 3 as inputs. So we're just going to add a third input. That's a video of Google Maps. And this should just work, right? So the great thing about training our model end-to-end is we should just be able to pass the map in as an input. And since the model is trying to predict where a human would drive, and the map has a lot of useful information about where the human is going to drive, the model should just figure this out. It should learn to use the map, figure out where you're going to go, when to take exits, when to make turns, and generally do whatever maneuvers are necessary to follow the route and get you to your destination. So this is what we built, and it works pretty well. So I'm going to talk a bit today about how all of this works, all the little details that make it work better, and all of the work we've done to validate this feature and get it ready to ship for OpenPilot 094. So I'll start with how it works. The first thing we're going to need if we want to build this is a good map. So fortunately, there's a lot of really good open source tooling we can take advantage of here. OpenStreetMap's overpass to serve up sections of the OSM graph, Valhalla for routing, mapbox.gl to render the maps. All of these tools have been really useful in building this. So we need maps. We train our driving models on a large data set of 60-second video clips. So we're going to need maps for all of those video clips. And again, the good news is OpenPilot already has navigation. The Comma 3 launched with built-in nav using the mapbox.gl native library. And so we can just use this same library in our data center, and we can render as many maps as we want. Mapbox.gl is pretty nice. You give it a latitude, longitude coordinate, you give it a route, and it will render a map for you. So you can see this at work here in OpenPilot, and we're going to reuse this same system. These are the maps we're going to draw. They're intentionally styled to be very bare bones. We just draw the road in white, the route to follow in gray, and we just draw these as 256 by 256 pixel images, 2 pixels per meter, so this is half a kilometer on each side. And these maps are nice and simple and easy to reason about. So we want to render a lot of these maps, and like I said, we need two things. We need the latitude, longitude for each map, and we need a route. So the latitude, longitude is easy enough. The Comma 3 has a built-in GPS, so we can just get the GPS coordinates from that. The route is a little bit trickier. So you can see here a visualization of a little chunk of the OpenStreetMap's graph. The junctions are marked in blue, and we have some GPS measurements from a Comma 3 marked in green with the X's. And you can see here that the GPS measurements don't line up exactly with the road. So they can be shifted a little bit, they can be noisy. For lots of reasons, the GPS measurements may not line up exactly with the OpenStreetMap's graph. So we need to fix this to get a route. What we want to do is take a list of all of the GPS measurements from one of these video clips, and we want to figure out which roads were actually driven on in that video clip. We want to match these GPS points up with your clip to the OSM graph, and then we want to snap those GPS points to the right roads. So fortunately, we do not have to do this ourselves. This is somewhat complicated to implement, but there's lots of services that'll do it. Mapbox has an API for it, but there's also an open source routing engine called Valhalla that does exactly this. This is called map matching. So you give it a list of these GPS points, and it turns it into a proper route marked in red, snapping all of the points to the graph and giving you the exact route that you drove. So this is exactly what we want. We've got our lat long coordinates, we've got our route, and now we can draw our maps. So now that we have our maps, we just need to feed them into the driving model somehow. The problem is, on their own, the raw maps are 256 by 256 pixels, so that's like 65,000 numbers. That's way too big. So we can't feed these directly into the model. We're going to have to squish them down somehow to make them a little bit easier to work with. So how are we going to do this? Well, we already do this for the camera images. Those have the exact same problem. So we have a neural network running on the Comma 3 that takes in a frame from the cameras and compresses it down into a vector of numbers. This is called a feature vector. And this vector should represent all of the details of the scene that are relevant for driving. So this is about 2,000 numbers for every frame of the video, and these get passed into the driving model. So we want to do something similar for the map model. We want to train some kind of neural network that's going to take in the map. It's going to compress it down into a vector that has all the information the driving model needs, and then we'll pass that to the driving model. So the way we're going to train this map model is as what's called an autoencoder. So what this means is that the neural network is going to have two parts, an encoder and a decoder. So we're going to feed these maps that we render into the encoder, and the encoder is going to squish these maps down into this little feature vector of a couple hundred numbers. And then the decoder is going to take those numbers and try to get back to the original image. It's going to decompress it and try to get as close as possible to what we originally put in. And if we train this all correctly, this feature vector should be a complete representation of the full image. It should have all of the details of the map that the driving model needs to know about. So we train this thing, and then we can just throw away the decoder. We don't need that. We just need the encoder. The encoder gives us some features, and we just feed those features into the driving model. So now we've got our nice squished down format. We can generate these map features. And you can kind of see here what the autoencoder is doing. So on the left, we can see the original maps that we render with mapbox.gl. And then on the right, you can see these maps after being squished and then decompressed by the neural network. You can see a little bit of detail is lost. It's not a perfect reconstruction, but it does a pretty good job at capturing all the high-level details and all of the information about the map that's necessary for the driving model to figure out where to go. So now we've got our maps, we've got our map features, and all that's left to do is hook this thing up to our simulator that Harold talked about, train a model with it, and cross our fingers that we did everything right and this will just work. So we do this, and it works pretty well. So you can see here, these are some videos from our simulator. The model's predicted path is in orange, and the real path driven by the human is in blue. So you can see as the model gets close to the exits, its prediction moves over, the model switches its trajectory to take the exit and follow the route just like it's supposed to. So this is great. We can do the same thing for turns. You see here, the model does a pretty good job. As it gets close to the turn, it adjusts its prediction so that it's going to try to follow the route. So this is fantastic. We have a driving model that's going to try to follow the route that we give it from the map. And now we just have to run this on the comma 3. So fortunately, this part isn't too complicated. We're going to add a few new processes to OpenPilot that'll let us do all of this stuff. So we'll add a process called mapsd and a process called navmodeld. Mapsd is going to render our maps for us using mapbox GL native. And navmodeld is going to take those maps, run them through our encoder, and get our map features out. And then we just need to make a little change to modeld, which runs the main driving model. We'll just make a change so it takes in those map features from navmodeld, it passes them into the driving model as a new input, and then everything else works just like before. So we do all of this, we put it on a branch, and it works. You can see OpenPilot is taking an exit here, following the route on the right, and if we've done everything right, this all just works. It works pretty well. So to give you a sense of perspective, this is roughly where things stood for the Taco Bell video at the end of last year. So we've been working a lot since then to get this ready to ship. It always seems to take longer to actually get things deployed and test all of the edge cases than it did to build it in the first place. So I'll talk a little now about exactly what it took to ship, and specifically some of the details that you have to get right to make this all work better, and some details that uncovered some bugs. So one obvious problem that you run into right away when you're building this stuff is that if you look at Google Maps or Bing Maps or any of these online maps and you just pan up and down, you'll see that the scale at the bottom right of the map is changing. It changes from 500 miles in the middle of the US all the way down to 200 miles for the same length at the northern end of Canada. And the reason this happens is because the Earth is a sphere and maps are rectangular. And so you have to take a spherical globe and somehow project it onto a rectangular map. And you can't do that perfectly. You have to make some compromises. So the way that most maps these days do this is with something called a mercator projection. So the mercator projection keeps these nice straight latitude and longitude lines, but the problem with this is that the areas near the North and South Pole get way blown up. So you can see this happening here. And for humans, this isn't really that big of a problem. But for a driving model, this is a little bit inconvenient because this model is going to use the map to predict in 3D space where it's going to drive. So without any extra information, the model doesn't know if it's making a turn in 200 meters or 500 meters because the scale of the map could be totally different. So we need to take care of this. It's not too difficult. We can just dynamically adjust the zoom level of the map to get a constant scale. So like I said before, we're going to render our maps at a scale of 0.5 kilometer on each side, and we'll change the zoom level as necessary to make that happen. Another problem we run into is that, well, we did all of this work to make sure that our routes were accurate to the road that were actually driven in each video clip, but we actually did too good a job. And so the problem is that sometimes when you're driving with your Comma 3, you maybe miss a turn, maybe you miss an exit, or sometimes you just don't want to follow the nav instructions. Maybe you think Mapbox is telling you to do the wrong thing, and so you just do something else. And the problem here is that with the way we've trained this model so far, it's basically never seen a wrong turn before. So the model is going to get super confused if you miss an exit. It might try to take an uncommitted lane change, or it might try to brake in the middle of the highway. All of these things are really bad. So we can't have this. We've got to fix it. So there's a couple different things that you can try, that we've tried. But what seems to work pretty well is we can generate these artificial routes that essentially have wrong turns in them. We can take the OpenStreetMap's graph. We already know exactly what route was driven in red. And so we can just pick one of the junctions in the video, go off in a different direction, and then do a random walk of the graph from there to generate these artificial routes. And we can train on a small percentage of these to make the model more robust. So there is a bit of a trade-off here. This is a delicate balancing act, because if you train on too many of these, the model will learn that sometimes it shouldn't follow the route, and so it won't be as diligent about doing the right thing and trying to follow the route when it can. But if you don't train on enough, the model won't be robust, and it can have bad behavior. So you have to balance these two things out. And we've found that training on roughly 5 to 10% fake routes maintains a good compromise between making the model robust while also not harming its performance at taking exits and turns. So now we have our model, we've fixed some bugs, and the last thing we have to do to get it ready to ship is write a ton of tests. We want to validate this behavior in all of the cases we can think of, in a bunch of edge cases, and we want to know exactly what these models are going to do when we deploy them. So, like Goff was saying, we have a saying at Comma that goes, "No testing in cars." And the reason for this is, especially for research, even though what we ultimately care about is that the model drives the car well, we don't want to test our models by putting them on an OpenPilot branch and seeing what happens. This is way too slow. If we have a model that we think maybe will be good, we don't really know, so we put it on an OpenPilot branch, we let some people drive on it, we drive on it ourselves, we gather a sample of data, and then maybe it turns out our model had a subtle bug in it, and now we've just wasted days or even weeks waiting for this data to come back so we can evaluate. So this is a huge waste of time. And so our rule, because of this, is no testing in cars. Instead, we try to write as many offline tests as possible. So before we ever put this on an OpenPilot branch, we want to have a pretty good idea of how it's going to behave when we do it. So these offline tests can take a lot of different forms. We can test by running the model on real driving data and seeing what it does. We can test the model in our simulator. We can test them in more traditional simulators like Carla or GTA. We can run a bunch of different tests in different cases and see exactly how this thing is going to perform. So what should we test for? Well, there's a few obvious ones. We want to make sure that the model takes exits when the route says to take the exit. So we can test that in our simulator. I showed some videos from that exact test earlier. We want to make sure that the model doesn't take exits when it's not supposed to. We want to make sure it takes turns when it's supposed to, doesn't take turns when it's not supposed to. We want to make sure the model doesn't misbehave if the route is incorrect, if you miss a turn or an exit, if the GPS location is a little bit wrong and it snaps you to the wrong road. We want to make sure that it doesn't misbehave if the bearing is inaccurate, so the map is like pointed the wrong way a little bit. We want to make sure that the driving behavior doesn't regress at all when you're not using nav, because we're just shipping nav in experimental mode right now, and so if you're driving in chill mode, we really want to make sure that behavior doesn't regress in any way, and if anything, it gets a little bit better. And we want to make sure that the behavior of these nav models is the same when we run them on the comma 3 compared to when we run them offline. So we do all these tests, plus a bunch more tests. We've spent the last few months just writing tests, and validating all the behavior we can think of, lots of different edge cases, and making sure that these models behave exactly the way we want. So we've finally written enough tests to give us the confidence to ship this for OpenPilot 094, and you can try it out today. It's available in experimental mode, and as we keep working on navigation and we drive the reliability up to 100, we hope to ship it in chill mode as well, so it'll be available for everyone that uses OpenPilot with Prime. So that's my talk. We can give time for a few questions.
All right. Jason over here.
I wonder if you could talk for a second about how speed limits figure in that you get from the maps. I know that you want the end-to-end model to function as independently as possible. You don't want to depend on map data, but do you foresee a future in using that as an input more consistently, especially when not navigating? I'm given to understand the mapbox API doesn't really lend itself to giving you speed limits if you're not navigating, but I think there was some sort of way around that with the Valhalla server. I don't know much about it, and I guess my question is really, long term, do you see that as an input or a hint into the overall driving?
Long term, I think probably yes. Right now, there's a lot of situations where the longitudinal behavior still isn't perfect. That has nothing to do with speed limits, so we want to fix that first. Like if you're driving on a highway and the model is only driving 55, you shouldn't need speed limits to know it's driving the wrong speed. So we want to fix that behavior first. Like you say, Mapbox's API is not super conducive to giving you the speed limits. There's a lot of areas where speed limits just aren't even available. But long term, I think there's a lot of cases where you can't really tell how fast you're supposed to be driving without the speed limit. So I imagine we will eventually need to add this as a model input, yes.
All right, got a question in the back.
Along the same lines, any thoughts on future input for real-time traffic that would then allow for, changing of routes?
Sort of. So Mapbox already takes care of this. It has its own traffic tracking system. And so ideally, the routes that go into the map in the first place should already take into account the traffic. Now, Mapbox's traffic system is not perfect. and it does sometimes over or underestimate the amount of traffic in a particular area. But hopefully this is something that'll improve over time.
Hey, have you put in any thought into like text-based navigation using like, I can see from your navigation that you have like take the next exit, for example. Like, do you guys use that as inputs ever?
Yes. So we have a branch right now that hopefully will ship for OpenPilot 095 after some more testing and validation that puts not just the map, but also the nav instructions into the model. And we find that this reduces the failure rate of the model to take exits and turns even further. So yes, this will probably be coming to a comma 3 near you sometime soon.
Thank you for your presentation. I just have a question. Have you ever considered using vector maps instead of these rendered BV maps?
Could you say again?
Have you ever considered using vector maps instead of the rendered BV maps?
Yes. So we do get the vector tiles back from mapbox directly, and so we could consider using those. And there are some advantages to that, in that there can be a bit of ambiguity just with the rasterized maps in some cases where you have a lot of roads really close together. So this is something we may look into in the future. Mapbox's tools kind of make it easiest to just render a map normally, and then you can just use normal convnet, efficient net to process this and compress it. With vector-based maps, maybe you'd want something more like a graph neural net. And these are a little bit more complex, and so we wanted to start with the simplest thing that could possibly work, but maybe this is something we'll look at in the future.
I used this navigation feature like a few days ago, and I found a problem when I used it. That it works for the first maybe a minute, and then it just quit by itself. Any explanation on that?
I'm not sure. We'll have to look at your logs. Maybe I can get your information afterwards, and we'll see if something weird is going on.
All right. Another question is, have you ever thought about using the map for the to the very original input? Maybe map it to the perspective view together with the image.
Oh yeah. So the autoencoder we train actually also predicts the trajectory that you're going to take, in addition to just compressing the map. It tries to predict in 3D space where you're going to drive. And so we could potentially use some of these additional outputs to show extra information on the driving view. But this is not a super high priority right now. This is something maybe we'd look at in the future as, you know, the main functionality of nav gets better and we have time to think about some cool additional features.
For the map encoder, is it trained primarily on a reconstruction loss, or is it trained jointly with the driving model, so it can more intelligently select which features are important?
It's trained separately. We do this for a couple reasons. One, because we want to run this model on the DSP instead of on the GPU. And so the map model has to be quantized. And so we train it with the quantization-aware hooks in PyTorch. Without this, it doesn't really work properly. And so in that sense, it sort of has to be trained as a separate model. And then also training full convnets with the sim is a lot of compute. And so it's a little bit easier to split it up. We have looked at doing it jointly as well, either with the vision model or with the policy model. But the autoencoder does do a pretty good job of capturing all of the details of the map. And so for now, at least, we think that it is probably doing just fine to just compress it to this feature vector and then have the driving model process it from there.
We've got one last question here.
So when you started the talk, you talked about how you at first wanted to just feed the video data of the directions into the model, and hopefully it would work, and then it worked pretty well. But I would think that there's like kind of an inherent conflict between the original video input and the map like directions input. Does the model just synthesize those two like magically, or do you have to really like weight them or like try to give inputs on which input is the primary to follow, or how does that work in the model?
You're talking about resolving like the video coming in with the map?
Yeah, the idea that the video tells one set of sort of inputs on how you should direct the driving output versus the map now suddenly might say, actually I want you to go this way. So I kind of feel like the two different pieces of information might give different outputs. How do you train the model to know which to follow and which in what circumstances?
Sure. So this is exactly part of the reason that we train on some percentage of these fake routes. We want to make the model robust to maps that either tell it to do the wrong thing or don't make any sense. And so when we always want to trust the video because the video is always right, or at least it better be, whereas the map could be wrong for any number of reasons. And so we do a bunch of stuff when we train these models to try to make them more robust to failures of the map if the route suddenly goes out or GPS suddenly goes out or any number of things that might happen, road closures, taking a wrong turn, all this stuff. So we really wanted to trust the video more than the map.
All right. Thank you so much, Mitchell.